Okay, welcome to GEOSLAM Part 2. Lauren is stuck in the VPR's office today, so I'll be introducing our speakers. This week we have 8 students. Each person will go for 7 minutes, sharing the cool stuff that they've been working on. And this week, when you guys finish your slides, go ahead and advance to the next person, and you all can come up and introduce yourselves. So 56 minutes total. First up, we have Colton Williamson. Yeah, space bar should work.
Okay, hello everyone. My name is Colton Williamson, and I'm working with Dr. Tip Solomon, trying to locate and quantify groundwater discharge in Farmington Bay and the Great Salt Lake. So a little bit about me. Like I said, my name's Colton. I graduated with my bachelor's in geology from the University of Utah. Before that, I attended Idaho State University until I got married, and then came to Utah and went to Salt Lake Community College and got my associates. I enjoy traveling and going to national parks with my wife, and we have a dog named Holly. My interests are in hydrology, specifically groundwater, and some of the big questions I've asked myself are how does groundwater interact with sediment and rocks, and how can we see that on the surface, and what does that tell us about our environment? So that leads into my project, which is how can radon-222, a radioactive isotope, help us in understanding groundwater discharge in the Great Salt Lake. So a little bit of background on Great Salt Lake. It's super important for Utah's economy. It extends our ski seasons, provides lots of jobs, and is a major pit stop on the migratory path for birds. So it's super important environmentally as well. But as we see in this figure from the GSL strike team, over the last 40 years we've seen a contemporary high and a record low. And to understand why this is happening, we need to look at the water budget of the valley and understand where our water is coming from and where it is going. So to understand groundwater, I've been using radon, which is a radioactive noble gas that decays from radium-226. It only has about a 4-day half-life and is produced in the sediments from radium in different sediments, minerals. And so the radon in the ground can get into the water column in a couple ways. One is diffusion, so it can just diffuse up through the sediments into the water and eventually into the atmosphere. This leads to pretty low concentrations in the surface. It can decay away so that it just never even makes it into the water, or it can decay in the water column. Or it can get into the water through advection, so that's the radon being dissolved into the groundwater and then discharging up to the surface. This leads to a high concentration that we can see when we measure surface water. So the big idea here is if we measure surface water and find high concentrations of radon, that means there must be a groundwater influence. Looking at preliminary data a little bit, we've taken about 200 samples so far in this distribution. We have some in Great Salt Lake, Farmington Bay, some of the surrounding rivers and tributaries and wetlands. And we end up seeing a couple of different categories of measurements. The blue bar represents lake background, so this is really low radon. It's not very interesting. It probably came through diffusion or just the flow of water. The yellow is rivers, and that accounts for most of our high measurements. But that green band in the middle represents the high radon concentrations we're getting from lake water, which are interesting to us. The histogram on the bottom shows just Farmington Bay samples, and you can see there's about 10 samples in that green bar that we're kind of interested in. Going through and sampling all these locations, we had to decide how we were going to sample. And one really cool aspect of this project is some interdisciplinary work using birds. So this figure was obtained through the USGS, and it shows where these avocet birds like to be. So in the red areas, they frequent the most, and the yellow areas, they don't go very often. And by sampling in the red areas, we're actually seeing a correlation between bird activity and high radon concentrations, meaning these birds like to spend time in areas that have possibly high groundwater flow, so the water might be fresher. We don't have a solid hypothesis of why yet, but it is an interesting correlation that is helping us sample. So zooming in on one of those red areas, we get this high density of high concentration radon water in the southwest bend of Arlington Bay. In this map, purple is really low concentrations, yellow is high, and we can see that that southwest bend has a high concentration area, so that's been of particular interest. We tried putting some seepage meters in there and didn't really get any concrete results, probably because the groundwater discharge is just so discrete, we have to pinpoint it exactly or you're not going to find any, and we haven't been able to do that yet. So we have a lot of measurements, but what next? I have created a MATLAB code that does an inversion on an equation that predicts radon concentration from groundwater discharge. So that's the forward model. Inversion tries us to flip that on its head, where we're going to use radon concentrations to predict groundwater discharge. Since we can go out and measure the radon, it's a lot more useful for us to know the opposite of that equation. So I've been using the steepest descent method, and that code has worked for synthetic data. So these graphs on the left side or right side, the top shows radon concentration against distance, and the bottom shows groundwater discharge against distance. Those red lines show the observed characteristics, and the blue is the model. And as the model progresses, you can see as the iterations go up, we get a better representation of the true model. So the goal is to apply this to real-world data and see what information we can gather from our radon concentrations. Finally, we're going to do a case study out at Antelope Island next week, trying to work on a small pond along the Antelope Island Causeway to see if we can use these techniques to pinpoint a good spot of groundwater discharge and further test our methods. And lastly, we need to further constrain the radon production rate and gas exchange velocity to know how radon is behaving in our system. Thank you.
Hi everyone, my name is Mallory McLean, and today I'm going to be talking to you about if cloud seeding can increase stream flow generation during snowmelt runoff. But first, a little bit about me. I come from the faraway land of Florida, the Sunshine State. I attended Florida State University and graduated with my bachelor's in mathematics and my bachelor's in environmental sciences. After graduating, I knew that I eventually wanted to go back to school, but I wasn't quite sure what for yet. So I took a couple years off and traveled across the country. I was living out of my car, rock climbing, and learned how to ski, and started working at Alta and realized that, wow, the mountains and the snow are really cool. I've never experienced this before. This is pretty awesome. I would love to stay here for a while, so I applied to the University of Utah and was granted the fantastic opportunity to study and be a master's student here. And when I told all my rock climbing friends that I was doing this because I just love the snow so much, they were like, oh, well, enjoy it for, maybe 10 more years and then it's going to be gone, which brings us to the motivation for my research, is that the climate is changing, and with the climate changing, snow is also changing. And since snow is changing, that means water's changing. Given that snowfall in the northern hemisphere is decreasing and projected to continue to decrease, 95% of water resources in Utah do come from the snowpack. So it's really important that we can find ways to mitigate these decreases and projected declines. So one way we've thought about this is using precipitation enhancement. One form of that is cloud seeding, which has been used in Utah, Idaho, and Wyoming for over 70 years now. Cloud seeding is essentially where we disperse silver iodide particles into an already existing cloud to give water vapor more material to condense onto and then fall as precipitation. So we're not adding water to the cloud, we're simply trying to increase the ratio of water that exits the cloud as precipitation. And so some research has shown that cloud seeding can increase snowfall, but there hasn't really been anything to show if it changes stream flow, and that's because there's very high variability in the relationship between precipitation and stream flow. even though precipitation on its own is the #1 predictor of stream flow, there's still a lot of variance in how much stream flow we get for a specific amount of precipitation. For example, in these Weber River catchments, which is where I'm studying stream flow, if we get 800 millimeters of precipitation in a given year, then we have a range of 100 millimeters to 500 millimeters. So it's really hard to predict how much stream flow we're going to get just from precipitation. And so there's lots of variables that go into stream flow, including precipitation, evapotranspiration, groundwater storage, and snowmelt dynamics. So if cloud seeding does affect stream flow, how are we going to be able to tell if the increase in stream flow is from cloud seeding and not some other variable like changes in groundwater storage? So groundwater storage is one of the variables that I'm looking into. It's a major driver of stream flow variability. Most stream flow during snowmelt is actually been found to be from storage. In different Wasatch catchments, we found that stream flow is anywhere from 5 to 12 years old. So instead of the snow immediately melting and going into the stream, we're finding that it probably percolates into the ground and is stored there for years before discharging. So when we look at groundwater storage and the amount of stream flow we get in a given year, there's very high synchronicity between the two. So if there's a lot of water being stored in the ground in a catchment during a year, then the same year the stream flow will probably be higher as well, and vice versa. If there's not a lot of water stored in the ground, we probably won't have as much stream flow that year. And so my goal with this, my objective is to quantify different variables like groundwater storage to see how they are influencing snowmelt and how it reaches the stream to determine if cloud seeding does increase stream flow. So I'm trying to determine the drivers of stream flow variability through hydrometrics, which is like mass and energy balances, basically the inputs and outputs and storage of energy and water in a catchment and in streams, and then using tracers as well to find the sources, routing, and residence time of water, essentially how a water molecule gets from the snowpack into the stream and how long that takes. And so my study areas, I have 2 larger catchments in the North Fork of Ogden and then Snow Basin. And Snow Basin will be our manipulated cloud-seeded catchment. North Fork of Ogden is our control. And then I'm looking at some smaller headwater streams where in Snow Basin, those ones will be cloud-seeded. And then this lower one, Peterson Creek, is in Wasatch Peak Ranch. I'm going to try and quantify these variables and see if I can see any sort of change in stream flow and if I can attribute that to cloud seeding. And hopefully through this research, it can lead us towards determining if cloud seeding does help us mitigate these projected decreases in snowfall and stream flow and apply that across the Western United States and other areas of the world.
Hello, my name is Ryan Lunt. I'm a first-year master's student working with Dr. Sarah Works, and my research is focusing on the impact of stream drying on downstream water resources. And before I get started, I just want to go ahead and acknowledge that research is a collaborative effort, and I would like to thank Dr. Sarah Works, England Palace, and Cameron Carr. They have all been very instrumental for the progress I've made so far, and I know they will continue to be as I continue with the project. Before getting into my work, though, I want to take a chance and go ahead and more formally introduce myself to the department. So I was born and raised in Maryland, just outside of Washington, D.C., and I went to my undergrad at Western Carolina University. And when I first started undergrad, I had no idea what I wanted to study. So naturally, I became a marketing major. And I was in this beautiful area, the Smoky Mountains, and I started getting outside a lot. I fell in love with trail running and mountain biking, and this idea of pushing myself really hard physically in beautiful, remote, rugged places. And this gave me an enthusiasm for the outdoors that I carried into outdoor guiding. And I fell in love with outdoor guiding and sharing this enthusiasm with other people. And this ended up taking me up to Glacier View, Alaska to work on the Madawaska Glacier. And it was here, I was like, whoa, water is really cool. 27 miles of frozen ice, and it was just like instantly, as soon as I saw it, came back to school, dropped out of marketing, and I switched my major to natural resource conservation management, and I've never looked back. And so getting into my project here, my project goal is to improve understanding of the importance of stream drying on downstream water resources by comparing spatial temporal drying patterns to outlet discharge. And for the sake of this project, we've went ahead and we've identified 2 study sites, one being in Red Butte, just behind campus here, and the other being in Albion Basin, which is in Little Cottonwood Canyon. And the reason we chose both of these sites is because they're very opposite ends of the spectrum when it comes to heterogeneity, both in underlying bedrock geology, topography, and vegetation. And this is very important and something we want to think about too, because we want to start identifying which, like a hierarchy of controls when it comes to stream drying, if a type of bedrock geology is playing more of an influence than another type of bedrock geology. And so kind of getting into the project, even though we have parallel experiments going on in both Red Butte and Albion Basin, for the sake of the presentation today, I just want to focus in on what we're doing at Red Butte. And so we went ahead and we've taken the initial watershed here, and we've divided it into 4 sub-watersheds that we're defining with each of these outlet points that we've chosen to collect discharge at. And through this discharge, what me, Elon, and Cameron did all last summer was we went out and we were collecting discharge measurements with standard salt injections, and from this we were able to compare it to stage level data. And this allowed us to begin to characterize what was going on with the discharge at each of these watersheds over the course of the season. And getting into the second part of my project, so discharge is commonly a collected piece of data, but something that's not as common is the absence or presence of stream flow. And we've gone ahead and at each of these circles here on the Red Butte map, we've deployed stream flow presence sensors at each of these sites. And from this, we're going back to Pine Fork, and this is a map showing, so at each of these circles here, we have a stream flow presence sensor deployed. And on the right here, from starting at PF1 on the y-axis, that's the closest to the outlet discharge. And as we progress upwards, we're getting further away from the outlet discharge. And on the x-axis here, we have date and months, and the blue is presence of flow, and the yellow is the absence of flow. And from this, we're able to get a better idea of how headwater streams are drying, and more importantly, when and throughout space. And so that's been a lot of the work I've done so far is synthesizing all this data, because what we have at Pine Fork, we have at about 8 total watersheds spread across the 2 sites. And what I want to do moving forward is I want to begin to quantify how time series are changing together through statistical methods to look at synchrony and figure out the degree of temporal correlation going on between each of the time series at the different sites. And secondly, I want to also go ahead and start characterizing and correlating the data we've gathered so far with different factors going on. So this is an example of a seismic image line we ran up in Red Butte this past summer. And I want to compare and see how what controls are having more influence over others. Thank you guys so much. That's all I have to share today. If you have any questions, I'll be around with the grad students at the end.
Hi. Today I'm going to be talking about sedimentation dynamics in Lake Powell, and my advisor is Dr. Carrie Johnson. So I'm Emma Kreis, and I'm from upstate New York. I've known I wanted to pursue geology since the 9th grade after I took earth science. And after I graduated from high school, I attended Binghamton University, where I earned my Bachelor's of Science in Geoscience. During my 3rd year at Binghamton, I took basin analysis and became super interested in the energy industry, so I knew I had applied to grad school. And I ultimately decided that the University of Utah was going to be the best fit for me because I really liked Salt Lake, my advisor, and I liked how my current research combines so many different aspects of geoscience, including geomorphology, sedimentology, and geophysics. And after I graduated from Binghamton, I attended field camp in the French Alps, which was super cool. And then a short time after that, I drove across the U.S. and joined Carrie in the field on Lake Powell. So my study area is Lake Powell, which is located in southern Utah along the Utah-Arizona border. More specifically, my research focuses on the Colorado and San Juan arms of the reservoir, which were impounded in 1963 by the construction of the Glen Canyon Dam. And my research has predominantly three guiding questions, including how fast sediment is accumulating, what do these subaqueous deltas actually look like that are depositing all of this sediment, and can stratigraphic principles help us predict delta evolution on human timescales. And my research has several broader impacts, both from a societal and scientific perspective, including sediment accumulation, as the USGS estimates that approximately 7% of storage capacity has been lost due to sediment infilling, which is important because Lake Powell supplies water to approximately 40 million people across western US, including Utah. And sedimentary processes have often been overlooked in reservoir management due to favor of hydroelectric power generation and water supply. And from a scientific perspective, Lake Powell represents a unique opportunity to study sedimentary processes on annual to decadal timescales under well-constrained boundary conditions, which help calibrate our deep time rock record interpretations and expand our knowledge on depositional environments. So the first tool that we're going to be using to study how much sediment is accumulating is multibeam, which provides high-resolution depth measurements of the lake floor. And this technology works by emitting sound beams towards the bottom of the lake, which then reflect back up to the surface. And from the time it takes for these signals to return, we are able to calculate the depth and shape the lake floor in super high detail. So multibeam and equivalents have been collected since the beginning of Lake Powell in 1963. And using that data, we can make diagrams like this one. So on the y-axis, we have the elevation of the lake floor in meters, and on the x-axis, we have the distance upriver from the Colorado-San Juan confluence. And these colorful, pretty lines are different time periods of sediment accumulation. So in the gray, we have 1963, which is pre-dam, and then moving up in time, we make it up to the red, which is from the most recent 2025 data collection. So you can see from this diagram that sediment is accumulating, and also the lake floor's morphology is changing. But you might also notice that you can't actually see what's going on the subsurface. So this project also utilizes CHIRP, which was collected in 2004, 2017, 2024, and 2025. And CHIRP stands for Compressed High Intensity Radar Pulse, and it is a sub-bottom profiling system that emits swept frequency acoustic pulse to produce high-resolution images of the near surface. And this is a sample line from 2017, and you can see the lake floor here, and then you can clearly see what's going on in the subsurface, which is going to help our interpretations of the depositional dynamics. So what's next for this project? Well, we're going to continue our interpretation of CHIRP and highlighting key sediment packages, and then we're going to correlate those sediment packages with the well cores that were collected by the USGS in 2018. Pending funding, we also hope to expand this study area closer to the Glen Canyon Dam to get a bigger picture of the depositional factors at play. And this diagram on the right, again, just shows the elevation of lake floor in meters on the y-axis and the distance upriver from the Glen Canyon Dam on the x-axis. So we're looking at about 0 to 15.5 here. And then data from 2004 is in purple, and 2017 is in pink. And I just wanted to show this to show why we'd like to expand the study area. Thank you.
All right, hi guys. My name is Michelle Norman. I am a first-year PhD student, and I want to tell you guys a bit about what I am doing for the next 4.5 years of my life here. So who am I? I'm a PhD student working under Chad Ostrander. I'm from all over the place, mostly the South, but I moved out to Utah in 2021 to get my bachelor's degree in geology from really far away from here at Utah State University. I graduated in the spring, and then 2 weeks later made my way downtown, and here I am now. Outside of geology, I'm interested in maximizing my outdoor bum time. I'm really into running, skiing, being outside, and recently just got an aquarium. This is my fish named Hank. He's kind of dumb. As far as my geological and academic interests go, I have been interested in deep time since the beginning. In my undergrad, I spent all 4 years of my time working in the Cambrian, doing a bunch of substrat and carbon isotope geochemistry at the poster child section for the Drummy and Stage Boundary out in Delta, Utah. I have decided to move further back in time for my PhD, and I am now working in the Neoproterozoic, which took place from about 1 billion to 539 million years ago. Again, I'm really into sequence stratigraphy and sedimentary rocks just in general. I think they're really cool. And then, of course, since I'm working with Chad, I also really like geochemistry. In my undergrad, I did delta 13C and delta 18O analyses, as well as some TOC analyses, and you can see that graph here. And then working in Chad's lab, I'm working with a whole suite of trace metals, and then studying non-traditional isotopes such as thallium. So my PhD is split into 3 parts at the moment, and the first main part of my PhD is doing redox reconstructions. So I'm working primarily in the Tonian, which is 750 million years ago, and I'm employing a bunch of different methods to reconstruct redox, but the main method of choice is stable thallium isotopes. So this schematic here kind of goes over how thallium isotopes work. The idea is we have a set isotope composition coming in from rivers, and then once it gets into the ocean, the thallium isotopes fractionate into 3 different reservoirs. We have an oxic sediment fractionation, a suboxic to anoxic sediment fractionation, and then a basalt alteration fractionation. Oops, my bad. Oxic sediments tend to fractionate thallium the most, so the presence of oxygen on Earth's surface is very well encapsulated with the thallium isotope measurements. And then this is just some preliminary data I have of trace metals working in the Uinta Mountains, which is not very far from here. Using different trace metals, I can get an idea of what the oxygen might have looked like without the isotopes. And as you can see, my preliminary data is plotting mostly in the oxic fields with a little bit below an oxygen minimum zone, potentially. Part 2 of my PhD is reconstructing modern salinity and developing a proxy that I can use in deep time. So to do this, I will be working in Holocene sediments from all over. So methods I will primarily be using include boron, gallium, and barium strontium ratios. This is a relatively new method to quantify general salinity in different sediments. It can't give you a part per thousand measurement, but it can classify salinity into different fields of fresh, brackish, and marine, as shown here. There are caveats to it. It's a work in progress, but it's a pretty foundational, and if we can get it to work very well in modern, we can potentially bring it back. And then, of course, epsilon 205 thallium. Chad has started developing a method where we have our oxic input of ocean water, and which is a marine environment, and our freshwater value, which is our river environment. And then we can plot a mixing line between the two based off of different brackish environments, and they roughly correlate with part per thousand measurements. These 2 points are anthropogenic altered basins, so these are 2 areas where this mixing line model doesn't work, but it is a development in progress. And then part 3 is taking what I'm doing in the modern and sending it backwards in time, once again to the Tonian. I will also be using boron, gallium, barium, strontium, and epsilon 205 thallium. I don't have my thallium measurements yet, but these are some preliminary data I have from the Red Pine Shale up here, which is in the Uinta Mountains in the Visingsö group in Sweden. These are roughly age equivalent sections, and as you can see, they plot mostly in the brackish to fresh field. Again, there are caveats, but it's pretty cool to have some preliminary data. And then I will also be doing some micropaleontology using a weird critter called a vase-shaped microfossil. This is a fauna that is abundant in the Tonian specifically, and you don't really see it in Earth history. outside of Newtonian. And there is emerging evidence that these fossils were deposited in a hypersaline environment. So I would like to pair kind of the geochemical side of things with the paleontology side of things and get a broader picture of what's happening with ancient salinity dynamics. As far as upcoming plans go, I'm going to be going to California soon, 2 different times to meet with collaborators in near LA, and then one of my committee members up at UCSB to do fossil taxonomy. And then I will be doing lots of chemistry. So this is Chad's new instrument up on the 4th floor. It just passed its install, so we're going to be using it soon. And then this is his new clean lab, so you should come check it out when you get a chance. And I will be doing all of these different chemistry things that you see here. But that's me. Nice to meet you guys, and I'm around for questions after.
Hello everyone, my name is Andrew Siciliano. I'm also a first-year PhD student working with Chad Ostrander, and the title of my GEOSLAM is Digging into the Details of Earth's Great Oxidation Event. So first, quickly, just a little bit about myself. I was born and raised in Las Vegas. I went to undergrad at the University of Nevada in Reno. I graduated in 2025 with a bachelor's in geology and minors in chemistry, stats, and climatology. I was super lucky to get to spend the summer of 2024 doing research in Chad's lab, helping develop some of the thallium-isotope methods upstairs. So I got like a 10-week window into what my PhD would look like. And I'm back for 5 more years, so I like my window. So my path is taking me from Vegas to Reno to Salt Lake, and luckily for my bank account, that means we've gone just steadily worse. I'm learning that, though, skiing is going the opposite direction. So the more you know, I think it's true always. Anyway, getting into my PhD, I've divided it into 2 main topics for this, at least for the early part of my PhD. The first, like the title suggested, is about the initial rise of oxygen at Earth's surface. So we'll talk more about this later, but just as a quick primer, can you see my cursor? Yes. The Great Oxidation Event is this here. This is the canonical sort of trajectory of oxygen concentrations over time. And my work will focus on this initial bump where oxygen rises for the first time by several orders of magnitude. But the second idea is improving our understanding of thallium isotope cycling in modern analogs for the ancient Earth. So like Michelle said, thallium isotopes are a paleo-redox proxy. So they are used to reconstruct past marine oxygen levels. And thallium isotopes and all paleo-redox proxies are applied through a uniformitarian assumption where we observe how they behave across a litany of environments in the modern Earth and then extrapolate back into the past. But the modern oceans look a lot different than the Precambrian oceans, so we kind of have to get creative and go to unique environments that have unique chemistry for the modern Earth that may have been more prevalent sort of in deep time to calibrate these tools. And so one such environment is the Mediterranean Sea, which on orbital timescales will go anoxic and sulfidic at depth because of increased runoff from North African monsoons. So this is on the right here, a core from the Eastern Mediterranean, and these anoxic events are represented by peaks in molybdenum concentrations. And so we'll study thallium isotopes across this core and learn about how thallium behaves across these sort of rapid environmental changes that would have been much more prevalent on the ancient Earth than they are today. And so we can better sort of calibrate this tool for its use in the deep time record. But getting back into the main focus, the Great Oxidation Event, the GOE, it's worth first considering sort of why is this important? Why do I care about this? In my case, I'm interested for its relationship to complex life. So surface oxygen is a prerequisite for complex life. Without oxygen, we would not be here today. And if we want to sort of consider the evolutionary transition that I have depicted below from single cell, simple life to exceedingly complex biological machines like Peter, that's my dog. Oxygen plays a forefront role in that discussion. So in order to understand whether or not this transition is likely to occur on a different planet, we need to understand what are the ultimate controls on the oxygenation of a planet. So Earth is our one analog to study, and luckily for me, this is an unsolved question. To sort of illustrate the knowledge gap visually, I plotted age on the x-axis and paleo-redox applications on the y-axis. This is the number of studies that have been published that are attempting to reconstruct oxygen broken out by type of proxy they used. We know that the GOV played out over hundreds of millions of years, but sort of right after the onset and before the end of this rise of oxygen, there is just very few studies that have been done, and so we don't have the data to say what's going on in the middle of the GOV. So put simpler, we do not know the trajectory of oxygenation across the GOV. So again, age on the x-axis, this time oxygen concentrations on the y-axis. What's shown in blue is what we have data for, what we can be relatively confident in. And there's about a Mesozoic-sized gap where we simply don't have any data. We do not know what's happening. And you can fill in these dots sort of any way you like. It might look like this, it might look like this, it might look like this. It could really look like anything. And you could imagine that each of these hypothetical trajectories would come with their own unique causes and consequences. So to understand why Earth got its oxygen, we need to fill in this gap. So that will be a major goal of my PhD, is to, using thallium isotopes and multiple sulfur isotopes, try and fill in this record. And so we've started to do this. Happy to share some preliminary results based on data that we collected and compiled from others. Most seminally, most importantly, is this bottom curve. The dashed line is showing our reconstructed trajectory of oxygenation. And most importantly is we see these multiple temporary episodes where oxygen does not rise monotonically. It will rise and fall, and when it rises in both the atmosphere and the ocean. And so what this means is for about 200 million years, the ocean was characterized by this transitional regime of oxygenation, as we call it, where oxygen was waxing and waning between only being available in these local small patches to being sort of omnipresent across the global surface ocean. And so you can also imagine this would have pretty unique evolutionary and selective pressures on a biosphere that may be seeing oxygen for the first time. Oxygen is pretty poisonous to certain anaerobic life. And lastly, this top panel shows the record of volcanism through time. Large igneous province events in units of megakilometers squared. It's a weird unit. But there seems to be this non-trivial association between large-scale volcanism, glaciation, and these temporary events. If you think about it, this makes sense. In the aftermath of volcanism and glaciation, continental weathering rates increase, nutrient delivery increases, and primary productivity increases. So it seems like these sort of solid Earth and climatological processes are acting as a major impetus towards oxygenating Earth permanently. And so by extension, may be important on any other planet that wants to have a GOE of their own. That's all I got for you guys, hopefully more soon.
Hi, I'm Melanie, and I'm doing my master's with Jim Carter, and I am looking at the pairing relations of CR2 chondrites, or CR meteorites from Miller Canyon Range in Antarctica. And just as a quick background, CR2 meteorites are carbonaceous meteorites. The R stands for Renazo, which is one meteorite that fell. That's part of this group, and they're just all named after that one. And then the 2 is the degree of aqueous alteration. So a little bit about me. I actually did my bachelor's here, and I minored in chemistry and ecology as well. I did my undergrad with Jim too. And after graduating in 2024, I spent a gap year traveling and working for Rio Tinto. And while traveling, I got to see really cool geology all around the world, and that made me miss studying. And then Rio Tinto made me realize I would rather be a student than actually work. And so what is meteorite pairing? So this is the process of identifying 2 or more meteorites that are part of the same ball. And our goal is to look at a total of 9 CR2 meteorites from 2 different sites, or 2 different locations, and try to pair them. So specifically, we're looking at meteorites collected from Antarctica. Jim is going to explain this a lot better than me, but they fall in this ice, they get covered by snow, they get buried in the ice is being pushed out, eventually it hits these mountains, and the ice gets abraded by wind, and the meteorites are pushed back out. And so they're found near these mountains on this old, dense blue ice. So for like the meteorite concentration area is going to be on that blue ice. And this study is important because we can understand the flux of meteorites, how they break up when they enter Earth, what types of meteorites are being found, how many, and most importantly for curation purposes, these meteorites are very unique and they're important to understand the origins of life since they're very carbon rich. And as you can see by that picture, there's a very small amount available. So if we're able to pair them, we can just have more available for research. So our samples are obviously from Antarctica, and this rectangle just shows the two different sites, and this star is Bermuda Station, where the ASMAT team that collects these meteorites, they start there and then they fly out to these different sites. And that rectangle is just that zoomed in. And this is where our samples are from, Miller Range, and our samples from Dominion Range. And as you can tell, they're on these dark gray areas, which is just that blue ice that I showed previously. And I just want to point out that they're fairly close in distance to one another. And by fairly close, they're like 300 miles apart. So the first method we're going to use is the easiest one, just analyzing the 5 locations, what they looked like in the field when they were found, and how close they were found to one another. And that picture just shows 2 different meteorites that they look really similar, so we might assume that they could possibly be paired. Then we'll do optical and electron microscopy, where we're going to analyze the texture, chondrules, model mineralogy, and chemical composition. And this is 2 different meteorites, again, in thin section, and they look very similar. Then we'll study bulk elemental and isotopic compositions, specifically HCN, and their isotope and abundances. And this is a graph from a different study where they're doing pretty much the same thing, just different meteorites, but from the same 2 locations. And they just plotted like the weight percent versus the isotopic composition. Then we'll do the CRE age, which is the cognitive ray exposure age, practically just the amount of time that the meteorite existed as a meter-sized object in space before entering Earth. So from the time it broke off the parent body to the time it entered Earth's atmosphere. And again, this is the same study, they just plotted age in millions of years versus the number of analyses. Oh, and we're going to do CRE age by measuring the noble gases and stable nuclides. Then finally, we're going to look at the terrestrial age, which is the abundance of positogenic radionuclides, specifically carbon, aluminum, chlorine, and krypton. So our 3 main questions are the meteorites from Miller Range paired, are the ones from Dominion paired, and could they possibly be paired to each other, especially because they're relatively close in proximity. So our next step, hopefully, is to get our samples soon, now that the government's open. And we're working closely with NASA, Rochester, Carnegie, and Purdue to carry out all these methods. And the picture on the far right is just us at JSC a couple years ago and the instruments we'll be using. Thank you.
Hi, my name is Tessa. I will be talking to you about interpreting uranium oxide ore processes using triple oxygen isotope measurements. Our affiliations are with the University of Utah and Oak Ridge National Laboratory, which will be supplying our samples, and the PI on this project is Isak. So a bit about me, these are my alma maters, and I played college soccer for A&M. The only time we really had a chance of beating any team was at LSU, which was where I went to school. I always knew I wanted to do my PhD, but I took a year off and worked in the industry. I did geosteering for shale gas rigs, and then for my second job, I did PFAS mitigation on Air Force bases, but I couldn't take a picture, so here's a picture of the truck I wrecked. And then last March, I married Brian, and now I started my PhD last semester. So why do uranium oxides matter? Well, they are essentially the core of the nuclear fuel cycle, the fuel inside of a nuclear reactor. They're also a key nuclear forensic material. The oxygen isotope ratios inside of a uranium oxide can record uranium's origin, manufacturing history, or processing environment. So in the background photo, we have 3 examples of uranium oxide. Yellow cake uranium is the most concentrated at about 70 to 90% uranium. And uranium has to undergo enrichment at enrichment facilities, and that then leaves specific chemical processes on uranium oxide that then we can pick up on. So why the triple oxygen measurement? Well, we stopped measuring what changed, which is what traditional delta 18O records, and started asking which processes caused it, which is what cap 17O records. So on the graph on the left here, we're looking at dependent mass fractionation between delta 17O and delta 18O, where we have a known slope of 0.528 or lambda, and this is called the terrestrial fractionation line. This is an average of where all Earth materials lie. Along this line, we can record temperature changes, fluid exchange, or redox conditions. So any deviations from this line is where we start to record different chemical processes versus just mass fractionation. So in the bottom left, these are chondrite materials. You can see that their deviations are quite large, and what we are trying to do is pick up on much smaller deviations from this line. So the equation right here, you can see that cap 17O is based on mass-dependent 17O and 18O. This small delta 17O comes from deviations, again, in the slope or lambda. So plugging in this cap 17O over here, we have it against 18O, and we can see that we get a specific solution to what processes uranium has undergone. This is what the results that we were trying to get look like. So again, like the results that we were trying to get, this plot shows that in delta 17O and delta 18O space, you get a clean separation by process, not just by composition. Movement across this diagram often reflects increasing fluid involvement or decreasing temperature. And basically from this, if Earth materials can separate cleanly in cap 17O, delta 18O space, then uranium oxide should be able to do the same with the different enrichment histories that they've undergone. So in the past, what we have used to do oxygen or triple oxygen isotope measurements is laser fluorination. Here are all the downsides, and we're moving away from it. Yes, that is a baby picture of Isaku. So it requires large sample sizes, hazardous reagents, and it is very destructive to samples. So fluorine gas is the most biggest problem with this because it is very hazardous. There's also user-dependent variable as well, so different users will probably get differing results. The way that this works is in the presence of fluorine, we heat a sample with a laser. That fluorine binds to the sample and then releases oxygen out in a predictable way, which then we're able to read the oxygen isotope. So overall, it is a safety nightmare. This is why we're leaving this behind. There's no accidents with fluorine, only fatalities is what the science community says. So from a research perspective, this really limits science. So the idea Isaku has proposed to NASA is to build a method that requires no fluorine. It will be the first one built here in the US at the University of Utah, which is pretty cool. So it requires no fluorine, no laser, and it's on smaller samples. Sorry. This instrument will be a fraction of the cost because, again, it has no laser, and instead of forcing out oxygen with weapons-grade halogens, we will heat it over graphite, and we will release CO or CO2 and convert it cleanly to O2 to get that oxygen isotope analysis again. So this is essentially the same science, but without the danger. It's lower cost and it's safer. There we go. So how does this aid nuclear forensics? Well, again, uranium has to undergo enrichment at enrichment facilities. This increases its potency, and it leaves specific chemical histories on it that then we are then able to pick up on. different plants have these different chemical histories. So this creates a traceability for forensic grain casework by tracking the movement of nuclear materials globally. Or if there's a spill of some sort, triple oxygen measurements add a unique solution or another dimension to a unique solution of what processes a uranium oxide have undergone. For the conclusion, or what we will get out of this project, is by adding the triple oxygen isotope measurements for uranium oxides, we're not just improving precision, we're also adding process level traceability that helps reconstruct where and how nuclear materials were produced. This will be the first non-fluorination CAP-17O data set on uranium oxides. And this method, once it's widespread, it'll enable safer and more accessible forensic tools. Thanks.
Cool, nice job to all the speakers and to Lauren for helping them put that together. Feel free to ask students questions individually in the last 10 minutes or so, but otherwise, see you all next week.